Okay, I wanted to go over some of the friction points that were on the quiz that seemed to cause some problems and confusion. I want to start with the boat question, where it says a boat sails north, which way is friction? So, some things that we kind of have to think about in terms of these friction questions and problems is where's the force that's causing the object to move, and then what's happening between the two surfaces. So if we have the sailboat here, here's the sail, and the convention that I'm using is north is to the right, south is to the left. So the wind is blowing this way and it's filling up the sail. So when the wind is pushing on the sail this way, the sail wants to go to the right, which means it's pulling the boat to the right, okay, which in this case is north. If we just look at the surface of the boat and the surface of the water, the boat right here, the surface is trying to go to the right, which means friction is to the left. And again, in this case, to the right is north, right? So you really want to focus on those two surfaces. Now, where I think it might get a little confusing um, is kind of like the person walking or running and the foot on the ground. So an example that's similar to that one, if you have a swimmer here and what they're doing is they're kind of grabbing a section of water in front of them and they're pulling that section of water and they're pulling and then pushing it behind them. Now, when they're pulling that section of water, if you kind of like just imagine the hand in the water right here, this is very, oversimplified example of what's really happening, but it might help understand some of the differences. So here, if this is the hand is trying to go that way, okay, which means the water is working against the hand. So the hand is trying to go to the left, and the water is resisting the hand. So in this case, the friction from the water is to the right, which also is the way that this person's body wants to move when they're swimming, in this case. Okay? So now the body, which is attached to the object that's in contact with the surface, there's one thing happening between these two things that doesn't mean the same thing is going to happen with the body. In other words, the way the hand is trying to move doesn't mean that's the way the body is trying to move. Okay? So to kind of like summarize it or try to like, break it down into a very basic way to think about it is you have your two surfaces that are in contact. You're either going to have a force that's pushing on one surface or pulling on that surface to try to get it to move in one direction. Whatever direction that object, that surface is trying to move, friction will always be in the opposite direction. So this is really what you need to focus on. You need to focus on the two surfaces that are in contact and what's happening with those surfaces. So if we go back to the person walking, running, whatever. So right now, this person, this foot is in contact with the ground. Now, the body wants to go this way. This is the direction the person wants to go. So now the muscles and the leg and the body, the torso and everything, they're trying to get this foot and shoe, they're trying to make this foot and shoe go that way, backwards or to the left in this case. So all the muscles in the body are trying to get this surface to go in that direction, okay, to the left. Well, if the shoe and foot are trying to go to the left, then friction is going to resist that. Friction will be to the right. So that's why friction is in the same direction that the body is moving, but it still is opposing the direction that the other surface is trying to go. Okay, so again, that's really where you need to put your focus, on the two surfaces that are in contact. Another question that caused some problems related to the electromagnetic forces that are involved in matter that cause friction. So, in one of the slide presentations, the videos, I was talking about, let's pretend that we could create two surfaces that had no microwelds. So, in other words, you could magnify them like a million times and you would not see any low or high points on either surface. They were completely smooth, completely flat, level, etc. We would still have friction, right? And the reason for that is all matter is made of positive and negative charges, electrons and protons. When you bring surfaces together, the alignment will change slightly for these electrons and protons, and causing a situation where the protons repel each other, the electrons repel each other, and then protons and electrons each attract each other. So it will create this kind of an alignment, okay, where you have a positive directly opposite a negative, and so on. Now, when you have that situation, you essentially create the peaks and valleys that we talked about. These are just electromagnetic peaks and valleys, right? So now you can think like a positive would be peak, right? That works against each other. Same thing with negative. That's like valley. That's not going to fit together. But when you have a positive, negative, those two fit together, and then that causes that locking that we talked about with the microwelds, that causes friction. So now if I try to move this surface in relation to that one, so let's say I try to move this way, well, all these electromagnetic forces in here are going to resist that motion, okay? And then when I do start to move it, well, then these are going to try to realign again, right? So if I move this in this direction, then eventually this electron right here is going to be opposing this electron over here, right? And that's going to cause a repulsion. And then that's going to cause, like, it's going to want to try to change and make this thing align so that the positive is aligned with it. So it's going to create like this movement with the matter and the electromagnetic forces that are involved. And then you're going to get friction. So no matter what you do, you're always going to have friction. And this is one of those things in the universe where they kind of like the universe doesn't give a free lunch. No matter what we do, energy is always going in a direction of less usefulness. And that's basically entropy and chaos. The universe is just going in one direction. Now, going back to the actual equation, this is still causing a lot of people confusion. Maybe people are just reading the questions too quickly, and they're just seeing numbers and they're just taking numbers and multiplying them. So we need to pay attention to these things. All right, so again, friction is mu times the normal force. Mu is a characteristic property of the two surfaces in contact. The normal force is how much the surface is pushing against the object at 90 degrees. On a flat surface, on a flat level surface, the normal force is equal to the weight. All right, so if this is I have an object here, 10 kilograms on a flat surface. The object has weight pressing down on the surface, and the surface presses against the object at 90 degrees with a normal force. So this would be my force diagram. Here's the object labeled mass. We have weight straight down. Weight is mass times gravity. The normal force is going to be straight up. There's no acceleration. So this is equilibrium. There's no net force. So that means that the normal force is equal to the weight, which in this case would be 10 kilograms times 9.8 meters per second squared, 98 newtons. So 98 newtons is a force. Sometimes the problems might be given where the weight is already given to you. Okay, so you don't have to multiply by gravity. All right, so here's an example of that. All right, what force is needed to keep a book sliding if the book weighs 33 newtons and mu kinetic is 0.115, right? So I'm telling you that the book weighs 33 newtons. I'm already doing the calculation of mass times gravity for you. So don't multiply gravity again. So just a quick sketch of this problem. We have a force that needs to keep this thing in motion. It's pulling it to the right. Friction is to the left. What is the force that's going to keep it sliding? All right, so it's not accelerating. It's just keeping it sliding. So that means the force of friction is equal to the force that's keeping it moving. All right, so this force is going to be equal to mu k times the normal force. We're already given the normal force, which is the weight of the object, 33 newtons. So 0.115 times 33, the force is 3.8 newtons to keep the book sliding. Okay, here is a solution to problem 10. I'm going to give you some practice and review problems. This is number 10. It's a little more challenging, so I figured I'd give you the solution so you could kind of see how one of these problems is done out. So you exert a force of 24 newtons sideways on an object, and it accelerates from 0 to 12 meters per second over a distance of 5.2 meters. You know that the mu kinetic is 0.58, so what is the mass of the object? Okay, so just a quick sketch. Here's my object. I'm making it a box, labeling it M for mass. I don't know what the mass is. I do know that there's a force of 24 newtons pulling it, right? That's the force that's being exerted on the object, okay? Friction is resisting in the other direction, and it's kinetic friction. We do have acceleration, right? It's accelerating in the direction of this force. It starts at rest, so it's at 0 meters per second. Then 5.2 meters later, it has a velocity of 12 meters per second. Okay, so some acceleration over this displacement created that final velocity. We need to figure out the mass. Okay, now we talked about this before. Net forces cause accelerations. So those two things have to exist together, right? If you have an acceleration, that means you have a net force, right? If you have a net force, it means that the forces do not add up to zero. If the forces do not add up to zero, you are not in equilibrium, okay? So all those things kind of work together, okay? Again, if you have acceleration, that means you have a net force, and that means you are not in equilibrium. Okay? So we write our sum of the force equation statement. Sum of the forces in the x direction equal ma. Okay? What are my forces in the x direction? Well, I have 24 newtons to the right, so that's positive. I have friction to the left, so that's negative. Those two things added together equal the mass times acceleration. Okay? Well, first, let's find out what acceleration is. So the equation that we're going to end up using, the kinematic equation from previous lessons and notes, v final squared equals v initial squared plus 2 times acceleration times displacement. The initial velocity is 0, so that cancels. We do some algebra, and we get acceleration is equal to v final squared over 2 times displacement. Plug in the numbers, 12 meters per second. We square all that, divided by 2 times 5.2 meters, and the acceleration is 13.8 meters per second squared. I'm going to save that. Okay, going back to my X forces, okay, 24 minus friction equals MA. Let's let's try to neaten this up a little bit. So that ends up being 24 newtons is equal to mass times acceleration plus friction, right? It's being added just because I brought it to the other side. So now the question now is, how do I figure out what the force of friction is? Well, kinetic friction is equal to kinetic mu times the normal force. The normal force, so in this case, the normal force is going to be equal to the weight of the object, which ends up being mass times gravity. Okay? So the normal force is weight, which is mass times gravity. All right? So I'm going to take that information and I'm going to substitute it back in over here. Okay, so mu times mass times gravity, I'm going to put it in over here. When I do that, this equation looks like this now. 24 newtons equals mass times acceleration plus mu times mass times gravity. I have mass in two locations, so I'm going to pull it out and put some parentheses there. Mass, parentheses, acceleration plus gravity times mu equals 24 newtons. Solve for mass. We get this equation, 24 newtons divided by acceleration plus mu k times gravity. We put in the numbers here, 24 newtons divided by the acceleration I found earlier, 13.8, plus 0.58 times gravity, 9.8 meters per second squared. We do all this math out, and we get a mass of 1.23 kilograms.